Myself, Dr.J Sirisha Devi, working as Associate Professor in Institute of Aeronautical Engineering College. In continuation to my previous talk on B trees, the previous lecture, I have given a brief introduction of what a B tree and how it looks like. In this lecture, we are going to look at the insertion and deletion of elements in a B tree. Let's look at the properties of a B tree and what a B tree in just a glance. So what is a B tree? It is a self-balanced search tree in which each and every node have m number of children. If it have m number of children, then it will have m minus 1 number of key values present in it. Or you can even say data value present in it. Right? So the basic properties that must be present in any B tree, or it must abide to these rules, are the property number 1. All the leaf nodes must be at the same level. Second one, all nodes except the root node must have at least m by 2 minus 1 keys and maximum of m minus 1 keys. Property 3, all non-leaf nodes except the root must have at least m by 2 children. And property number 4, if the root node is a non-leaf node, then it must have at least 2 children. And property number 5, a non-leaf node with n minus 1 keys must have n number of children, which I was telling just now. Property number 6, all the key values in the node must be in ascending order. Okay, it is also known as a height balanced M-based search tree. Guys, if you want more brief intro of the same, please do watch my previous video on introduction of B trees. Have a look at this example of B tree order 4, means 4 children and 3 keys. Look at each and every node and its corresponding children. You can see that all the left-hand children of any key value will be less than the key, and the right children will be greater than the key, right? The same property of binary search tree. Please remember, even if you say AVL tree or multi-way search tree like your B tree, every tree is a binary search tree in itself. So it must abide to the property saying that all the left children are less than or equal to the parent, whereas the right children are greater than the parent, right? So what are the operations that we can perform on a B tree? Search, insertion, and deletion. The complexity of all the 3 operations are of order log n. Okay, we go off log n. So let's look into each and every operation keyly. Search. Have a look at the algorithm. So initially read the element which you want to search for in your B tree. So hold the root node first of all. As the root node, as the elements are placed in ascending order, compare with each and every key value present in your root. If there is a hit, that means if you found a match of the element which you are searching for, then it is fine. The search is over. Or else, identify the key which is having a value nearer to your search value. So if a match is not found, search for an element smaller or larger than that key value, as I said. So go to step number 5. If the search element is smaller, then continue the same process with the left subtree. If the search element is larger, continue the same process with the right subtree. Same, okay, left or right. Repeat the same process taking from your step 2. From step 2 to step 6. Unless you reach the leaf nodes. Once you reach the leaf nodes and you still didn't find the element, then simply you can say that the search element is not found and return. Okay, or else in between you will find your search element. This is a simple search algorithm. As we are not going to manipulate or update or change anything on your B tree, the tree will be as it is. Let's start our insert operation. look at the algorithm of this one. So the basic point which you need to remember always is we add a new element only at the leaf node. Only at the leaf node. Only leaf nodes have the capacity to accommodate new nodes in a B tree. So, as the first property of B trees says that all the leaf nodes must be at the same level, we adjust the key values. Few key values will be traveling towards the root to balance the same. Height balance a tree as B tree is, right? So, first of all, check whether the tree is empty or not. If it is empty, then create a node with the key with which you want to insert and say that it is the tree. Or else, if it is not empty, then find a suitable leaf in which you can place by simply using search logic, which we have seen just now. Now, while inserting, you need to be very careful. If that leaf node has empty position, then it is fine. Add the new key, okay, in the leaf node in the ascending order. Guys, please remember each and every node, all the keys will be in the ascending order. Now, if that leaf node is not empty, it is full. Say it can accommodate 4 keys and all the slots are filled. What you have to do? You have to split that node into 2 halves. How we are going to split is split that leaf by sending the middle value to its parent. Repeat the same if the parent is also full in nature. Okay, split the parent also. This you are going to do unless you reach the root. If even the root is full, divide the root into 2 halves and take the middle element and make it a new root node. Okay, so this is a splitting procedure which we adopt if we do not find a place for a new node. So this you can repeat it and you can even split the root node also as given in the step number 6. I'll explain you with all these steps with an example. Have a look at this example. So I'm going to construct a B tree of order 3 for the numbers 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So order 3 means what? Order 3 means it can have 3 children. 1, 2 and 3. And how many keys it can have? It can have 2 keys. 1 and 2. Then what will be the nature of the children? All the left children of the first key will be less than key 1, or say K1 and K2. I'm naming them also. Okay. Let the children be C1. Then the children C2 will have a nature saying that all the key values in C2 will have values between K1 and K2. Right? So let's talk about child C3. Child C3, all the node key values will have a value higher than K2. Okay, so this is a property which we have already seen in binary search trees. Remember, binary search trees tells that left node must have a value less than the parent, right node must have a value greater than the parent. Okay, so let's do this. So when I insert 2, so as a node can have can accommodate right now 2 keys, and that too in ascending order, insertion is fine. Now, if I want to insert 3, problem arises. So, in this particular node, only 2 keys are there. It cannot accommodate third one. So, I have to raise or take the middle one to the top and make it as the root. So, I made 2 as the root and 1 as its left and 3 as its right. See, in B tree is still abiding to the rule of BST, right? Binary search tree. Now insert 4. No problem. The right node of 2 can accommodate 4. What happens if you try to insert 5? When you try to insert 5, as per the rule, it must go and sit beside 4. But can this node accommodate 5? It cannot accommodate. So we have to send its middle element 4 to the top and split the nodes into two halves. Have a look at this one. So I have split. Look at the natures of the key values. The key values in this node are less than 2, and in this subtree are between 2 and 4, and in this rightmost subtree are greater than 4, right? So let me insert 6. No problem. When I try to insert 7, the problem raises because this node cannot accommodate 7. So I'm going to split this into two halves and I'm going to send 6 to the top. If I send 6 to the top, even the root cannot accommodate because it have two keys which is fully filled node. So what is the middle value? 4. This 4 I have to bring it to the top and make a new root such that its left node is 2 and right node is 6. Have a look at this picture. So 4 is the new root whose left subtree is headed by 2 and right subtree is headed by 6. Right? Great. Let's insert 8. No problem. 9. Again, a problem raises as this node cannot accommodate 9. So as this cannot accommodate 9, I'm going to split it and send 8 to the top. So when I send 8 to the top, the right subtree of 4 is fully filled. Right? Now 10. Now you can see that while inserting 10, no problem. Everything is clean. So this is how we are going to construct a B tree of order 3. Let me take in another example of order 4. Okay, you can see random values are there. It is of order 4. What do you mean by order 4? So it can have 4 children. 1, 2, 3 and 4. How many keys? 3 keys. Say K1, K2 and K3. Okay, then what about the nature of children C1? They'll have values less than K1. What about the nature of children C2? They have the values between K1 and K2. Coming to children C3, they have the values between K2 and K3. Nature of children C4 is they'll have values higher than K3. Please remember these points while inserting the data. And the basic point is each and every node, all the key values will be in ascending order. Okay. So if I insert 5, fine, no problem. When I try to insert 3, as 3 is smaller than 5, 5 is going to jump towards right and 3 will be accommodated in the first place. Coming to 21, no problem. It is been seated at the last. Coming to 9. What is the actual place of 9? If you try to insert in the list of 3, 5 and 21, it is going to sit between 5 and 21. Am I right? I have shown it in the picture. So as we have seen this, 9 cannot be accommodated because there is no space. All the 3 keys are full. So we have to split it into two halves. So the elements are 3, 5, 9 and 21. If I split it into two halves, I have to take 9 to the top and make it as the root node. Right? So let's do the same. I am going to take 9 to the top and I'm going to split it. When I split it, so 3 and 5 will be on the left side and 21 will be on the right side. Okay. So now, guys, remember, whatever the size may be, whatever the number of elements may be, you have to pictorially show all the keys and children. Okay. Even if they are empty. Next, insertion of 1. As 1 is going is the smallest element currently and it will come left to 3. No problem in shifting the positions of 3 and 5. So we have shifted and accommodated 1. Right? The next element which I have to insert is 13. As 13 is greater than 9, it will come as the right child of 9. Right? In the right child, we have a subtree where 21 is already existing. As 21 is greater than 13, it is going to shift towards right and accommodate 13. So, successful insertion. Okay, next I want to insert 2. So, in the order, if you see 1, 2, 3 and 5. 2 is supposed to sit over here, but it doesn't have the space. The node cannot accommodate. Now, I am going to split it into 2 halves. If I split into 2 halves, the middle element is going to the top. That is 3. When 3 goes to the top, it is the duty of 9 to shift. It is the duty of 9 to shift 1 step towards right and give space to 3. Have a look at this. So, if I split, so 1, 2 will come as left and 3 will go as right. But remember, all the values 1, 2, 3, 5 are lesser than 9. So, everything will come on the left of 9. So, this is how they are divided. Have a look at the second picture. So, 3 and 9 are at the root. All the left elements of 3 are lesser than 3. Right elements of 3 or left elements of 9, you can call it in either way, are between 3 and 9. All the elements right to 9 are greater than 9. Right? I hope you understood till here. Next comes insertion of 7. As there is no problem, simply insert it and place it beside 5. The node can accommodate. Next comes insertion of 10. When you try to insert 10, 13 and 21 are going to shift right and accommodate 10. Next comes insertion of 12. Have a look. 10, 12, 13 and 21 is the order. But the node cannot accommodate 12. So I am going to send 13 to the top. Look at the picture which I have given you. So 13 is going to the top. So once 13 goes to the top, it will be given a place like this and its left will be 10 and 12 whereas right will be 20. Let's see it pictorially. Have a look at this one. So if you keenly look into this one, all the keys and children are abiding to the property of B tree. So all the elements right to 13 are greater than 13. Left to 13 are between 9 and 13. Okay? Right. Next, insertion of 4. When you try to insert 4, as it is a value between 3 and 9, it must come in this node. As the node can accommodate, it is having an empty space. And as the key values must be in ascending order, 5 and 7 are going to shift 1 step towards right and give space for 4. Okay. Next, insertion of 8. When you try to insert 8, the order will be 4, 5, 7 and 8. But the node cannot accommodate 8. So the middle value 7 is going to go to the top. When 7 is going to go top, the order must be 3, 7, 9 and 13. Even the root cannot accommodate it. So its middle value 9 is going to go to the top, creating a new root node and splitting its children into halves. Let's have a look at this picture. So 9 went to top. Its left and right children are 3, 7 and 13 respectively. Then left of 3 are 1 and 2. Right are 4 and 5, which is the value between 3 and 7. Right of 7 is 8. Coming to the left of 13 is 10 and 12. Guys, all the elements which are right to 9 must be greater. Okay. Then left of 13 is 20. Okay. This is how we are going to perform insertion operation in any B tree of order M. Here we have seen two examples of order 3 and order 4 respectively. Let's, I'm giving few sample questions. You can make a note and you can implement it. If you have any doubts, please throw your doubts in the comment section. Okay, guys? Then, deletion. This is the third operation that we can perform on B trees. Then, so in the time of insertion, if the node cannot accommodate, we split it. So, the other side of the coin, we are going to see now. After deletion, what if it is not having enough children to maintain that node? We are going to merge the nodes. So have a look at this algorithm. So locate the leaf node first of all using the basic search operation. Locate the node. So if there are more than m by 2 keys in the leaf node, then you delete the desired key one. Okay, the desired key which you want to delete. There will not be a problem. But if the leaf node doesn't have half of the keys, then you have to take either one of the steps. So if the left sibling contains more than half, then largest element, then push its largest element up to its parent. Or, so if the right sibling contains more than half elements, then push its smallest element. So as it is right side, the smallest element can be sent to the parent. Okay. So this is a small algorithm. Let's see it through animations. Okay. And we do have another case where neither left or right have the capacity to break or to merge. Then what you are going to do? So in that case, we are going to merge them into two halves into a single half and send intermediate to the parent. Okay, so have a look at this example. I have taken this tree. Let's see the deletion operations. Have a look at this picture keenly. Guys, all the left children are lesser than the parent. All the right children are greater than the parent. And each and every node, the keys are in ascending order. So what order it is? As it can accommodate 3 children, it is of order 3. 2 keys, 3 children. Okay, order 3. So delete 65. If you delete 65, no problem, balanced one. What if you delete 70? When you delete 70, have a look at the previous one. What if you delete 70 over here? If you delete 70, what will happen? When we do that, we need to merge because neither left nor right can send its value. If 60 is sent to the top, it will lose the left element. If 80 is sent to the top, it is going to lose its right element. So to overcome that, we merge 60 and 80 so that all the left elements of 90 are lesser than 90 and right elements are greater than 90. Okay. Then what if I delete 100? No problem. If I delete 100, which is the right child, so simply I'm going to break 60 and 80, send the 80 to the top and bring the 90 as the right child of 80. We need to balance it at any cost, seeing that it has minimum half of the children, m by 2 children, if the order is m. Okay. So what if I delete 80? Delete 80, not a problem. So 90 is there still. So you can have that. So another example of deletion. Have a look at this one which we have seen in the previous example. Okay. So delete 6, no problem. 4, 5, 6 were there. Even if you delete it, so half the children are still there, not a problem. So if I delete 13, for 14 and 15 are going to move front and not a problem. So what if I delete 7? So when I delete 7, when we delete 7, what you can do? So if I delete 7, Either you replace it with the largest value, that is bring 5 to the top, or smallest element on the right, 10 to the top. You have two options over here. Either one will serve the purpose. For example, what if you try to delete 23? So the largest element in its left child, which is 22, or the smallest element in its right, which is 24. Replace it with either one of them. It is fine. Okay. Then what if you delete 20? If we delete 20, we can replace it with either 19 or 21. 21 is the smallest of its right child, whereas 19 is the largest of its left child. Right? By this, I hope you understood deletion operations in B trees. So, in this session, we have seen a snapshot of what a B tree is, what are its properties, and what are all the three operations that we can perform on B trees: searching, insertion, and deletion. Guys, please do remember the basic properties of B tree when you insert or delete. Order is very important. Order tells you the number of children it can have, and the data inside a node must be in ascending order, and the property of minimum half children must be there for each node except the root. Root node have this concession. Okay, thank you. I hope you understood this session. Thanks a lot.
Like, share and subscribe. Hit the bell icon for more updates.